Field of power conversion devices. That's AC to DC for the novices out there. He's primarily responsible for the resurrection of this technology, quite frankly. Tesla's bladeless power conversion techniques and the next generation thereof. With that, please welcome Jeffrey Hayes.
Thanks, and glad to be here at Exotic Research, and glad that Steve Ellswick has hung in there and kept this going for us. So I think he deserves a lot of credit. Anyway, what we're going to do today here is talk a little bit about the Tesla turbine, how it operates, what its applications are, what its implications are, and hopefully take a lot of your questions during the session. How many people here are familiar with the Tesla turbine? How many have heard of it but don't know how it operates? Okay, good percentage. So we're going to start at the basics and take you through it and let you know what Tesla called his greatest invention. Most people don't realize what Tesla did after 1900. If you look at these documentaries about Tesla's life, it generally stops at around 1900. Most people don't realize that he was productive all of his life. And this is the technology that he worked on after that period. He built his first turbine in 1909, and he didn't stop working on this until his death. He never gave up on this. He said this was the engine of the future, and he was totally convinced that this would solve our energy problems. Unfortunately, it got distorted. People that tried to reproduce it didn't know what they were doing. They did. It's such a simple machine, but they managed to screw it up. One bright spot about it, it did get into industry for pumping. It is the best pump you can buy. There is no better pump. It is the finest pump available for any money. You might ask, well, why don't we see it then? Where is it? Why don't we know about it? Well, the industry knows about it. The big dollar people know about it, and that's why it's not used. It's such a good pump that they've got the price so high that it's not in general use. Okay. Any questions at this point? Don't know enough yet. Okay, basically all a device is a series of disks keyed to a shaft. In this photograph here, you see his basic turbine. This is out of the first publication that we put together. It was called Boundary Layer Breakthrough. That book was published in 1990. It was the very first book in English on the turbine. So in 1990, we started the resurrection process. Okay. We've since come out with a second edition of that, which is called Tesla's Engine. This was published in 1994. Okay. But basically, all a device is a series of disks. You see here, this is a pump rotor, and there would be a shaft mounted on the back here, and the shaft is driven. You can't really see it very well here, but there's a hole right here. Okay. Here's the patent drawing. And you'll notice it's very similar to any other kind of centrifugal pump. It has a volute-type housing. It has a series of disks stacked and driven by a shaft. In this case, Tesla has got these center spokes. These are almost never used in, well, they are never used in the industrial pumps. Why is this such a good industrial pump? Why is it the best pump that there is? There's no tight tolerances, that's true. What's his main claim to fame? Does anybody know? It'll pump solids, right. It'll pump a solid, it'll pump a liquid, it'll pump a gas, all at the same time. It's an amazing pump. The commercial ones that are available, they actually have the disc taken apart that wide on some of the models, or wider, and it can actually pump solids that will fit into that hole.
You can even pump fish.
You can pump live fish, right. It's about any kind of solid will go through it. There's a company by the name of DiskFlow that's the main action on this. They actually claim patent protection, incorrectly in my opinion, but their main patents have expired now, so there's really no more problem with that. But they've really taken the technology and proven it. Matter of fact, Texaco claimed in 1988, when they started using this technology, that they were saving $68,000 per year per pump that they had replaced with this technology. So this was in Chemical Processing magazine, and here you see the pump being electrically driven. There's a motor, it drives the pump. And previous to this technology, they had to replace these pumps on a very regular basis because they were pumping some of the nastiest stuff imaginable and would destroy their blades in their pump, because conventional pumps use blades. What else doesn't happen with this pump that happens in conventional bladed pumps? Cavitation. What is cavitation? It's an implosion, right. Whenever you suck on something, what happens? The vapor pressure will, you're actually drawing a vacuum, right? And what happens when you draw a vacuum on a fluid? It starts to boil, right? If you go higher in altitude, what happens to the boiling point? It goes down. So in these pumps, especially in applications where they have a high vapor pressure, that fluid will boil very easily with any kind of vacuum applied. Okay? When those bubbles form, the blade comes along, and what does it do to that bubble? It punctures it. Then all that stored energy that it took out of the environment in that boiling process is now released instantaneously. And what that does is a tremendous implosion force, and it will eat away at those blades. Every bubble that pops is eating until there's nothing left. So if you have an application where there's a high vapor pressure in your fluid, this is really the only pump that will survive, because cavitation will destroy any pump. Okay. Questions about pumping? The turbine did not really need assistance in this regard, because that had been pretty much developed and accepted. Where it wasn't accepted was for the heat engine, because any pump can also be used as an engine, right? If it's an efficient pump, and it is an efficient pump, it should, by all rights, be an efficient engine. Where the guys that were doing the pumping had declared, and they're a multi-million-dollar operation making these pumps, they declared that it was no good as a heat engine, because they had attempted to make it work, and they couldn't make it work, and if they couldn't make it work, it was no good. Okay? And they had not seen the original Tesla work. They had not taken the time to investigate to see what the history was. They just declared it unworkable. The main reason was because in 1977, Conoco drilled a geothermal well, and they wanted to test this technology, and they built the turbine for Conoco, and it didn't work. They didn't build it right. So how does the turbine work as opposed to the pump? Well, the pump, go to the viewer, the pump sucks in the center. The fluid is accelerated in a spiral. It's thrown out by centrifugal force and comes out the outlet. So you drive the shaft, you have the sucking actions through the center, and then it takes it out the periphery. Well, the turbine is just the opposite. In the turbine, what you do is drive the shaft. You have the fluid coming in here and then exiting out the exhaust. Just the opposite. So the geometries are slightly different. Here's the patent drawing for the turbine. And this is really all those guys went by. This is really all they had when they tried to make this. When they tried to make this device, they really didn't have any more than this drawing right here. But you can see in this, here's the nozzle coming in. High pressure fluid comes in here, vortexes around, and comes out the center. Now there's two nozzles here. Why is there two nozzles on this? One is reversing. Right. On conventional bladed turbines, they'll typically have more than one nozzle, correct? They'll have nozzles all around. You can do that on this unit also, but Tesla never did that. He didn't have to. Why didn't he? Why does a conventional bladed turbine need multiple nozzles, but the Tesla turbine generally only needs one? In a way, but what's happening in there? you'll notice that the fluid comes in, it's going to vortex around in a circle and hit all areas of that disc. And if you're hitting all areas of the disc, do you want to have multiple nozzles? Because in the bladed world, what they do is they put the multiple nozzles in there to get more action because you're only getting action at one spot. In the Tesla turbine, you're getting action all around. As it comes in, you get action spiraling around. It's a vortex, and it's just wringing the energy out. So there's two forces acting here. It's still acting as a pump, correct? It's moving around. There's still centrifugal force, right? Trying to force the fluid out, right? Well, there's also fluid coming in trying to push the fluid in. So wherever those two energies meet is where the fluid is going to be. Right here you have a high pressure at the periphery. You have high pressure here. As it loses some of its energy, it's going to come in to a lower point in the disc. You have less centrifugal force, so it's always going to be in its appropriate spot. And that's how the vortex works. Okay? So you're always hitting all areas of that disc. If you want to reverse, you simply close this valve, you open this valve, and you instantly reverse. It's the only turbine that's reversible in that manner. With blades, you have curved surfaces that are... go back to me. Okay. There we go. In bladed devices, you have curved surfaces. The blades are curved, right, one after the other along that shaft. The fluid comes in and hits that curved surface. If you want to reverse the turbine, what are you going to have to do? You're going to have to hit the opposite side, and that's not the geometry that they want to hit, so it doesn't work. Question?
Yeah. In relation to the amount of head it can handle, in relation also to piston pumps, vane pumps, those kinds of things,
How does it compare? The question is, how does this compare in providing pressure? To get high pressures out of this device, you'd have to stage it. You have to actually go to multiple stage pumps if you want high pressure for pumping. And that's been done. Go to the viewer, please. Hello. Switch. Cameras, please. There we go. Not that one. Overhead. There we go. Tesla actually got a patent for multiple stage pumping. You'll notice here that there's multiple stages. You go into one, comes out, goes into the other, and so on. This line means, here, this empty spot means you can insert as many stages as you want. Aerojet built one of these for pumping liquid hydrogen. Very similar, you'll notice. Input here. Of course, they changed it. They took its center geometry out. It's just a hole there, but it comes in. Whoops, I'm backwards here. It comes in here and goes through the stages and comes out here. On this, they were able to get, does it say 140,000 RPM? This is 1 inch. This is just a 1 inch rotor. It's 15 gallons per minute, 3 stages, head rise to 24,000 feet at 1 inch diameter. So it can pump some pressure. Any other questions? Question?
How is the force transferred to the rotor? Is that purely friction of the fluid over the surface?
Good question. How does the energy transfer from the fluid coming in to the rotor? It's not friction. If you have friction, what do you have? Heat, and heat means loss. There's a professor at Tempe State University here in Arizona who did a lot of work on this. He was the premier academic that was looking into this. And he measured rotor efficiency. Does anybody know what he said the rotor efficiency could be as high as? Well, it's in percentage, 100% being the best, 0% being the worst. He claimed that the efficiency could be over 95%. Tesla claimed 98 plus. So it can be very efficient if built properly, and that's the key. It has to be built properly. Okay?
You haven't yet answered how the force is transferred.
You're right. I haven't answered that question. Oh. The force is transferred by two elements. Here's a turbine disc here. And the way this works is by adhesion and viscosity. If I took a drop of water and put a drop of water on this plate, what's going to happen with that water? Is it going to fly away? It's going to stick. That's called adhesion, right? it has a relationship with that plate electrically. It wants it. It wants to be there, right? Sticks. It doesn't fly apart into separate pieces and stick all over the disc, does it? It sticks together in, it's not only attracted to the disc, it's attracted to itself, right? And that's called viscosity, right? The more it sticks together to itself, the thicker it is. And that's called viscosity. So it works by two concepts, adhesion and viscosity. And Tesla said the real beginning of this technology is when he realized that. When he made a single disc for pumping mercury. And he initially thought that it was a frictional effect. It's intuitive that you would think that. And then he says, no, one day I thought it out and I thought, no, the fluid isn't always sliding by, it's carried along and accelerated to the same speed. So it can't be friction, because friction takes a differential of speed. So it must be adhesion. And that, you see, was the real beginning. And that's when he knew he was onto something. Because it's not a frictional effect. It's adhesion and viscosity. Does that answer your question?
Yes.
Okay.
Are you familiar with the work of Jake Bussell?
I'm very familiar with the work of Jake Bussell. Matter of fact, the first book I did called Boundary Layer Breakthrough was much related to his work. At that time, Jake was the only person that was really doing anything with turbines. Not correctly. He was the person that was involved with that 1977 Conoco test that failed.
I thought he had some very good success with geothermal.
No, that's not true. I have the video from that geothermal test, and there was plenty of steam coming out of that well, but it went right to the turbine, and it did not turn. And I'll explain why.
Is he still alive?
No, Jake has passed away. I have to give Jake a lot of credit, though. Even though he didn't do things correctly, he was our inspiration. He was at the 1984 Tesla, was it? 86. At 86, he spoke at the Tesla Society, and that's what got me going. So I give him a lot of credit, even though he wasn't into Tesla. That's the problem. The only success that's been had on this is when we go back and give up our ego and say, okay, I don't know anything. What did he say to do? Unfortunately, that's not the way people have approached it.
He also worked on a jet engine and compressors on the same technology.
Yes, he was working on jet engines, and none of that worked. None of that worked. Other questions?
If adhesion is a property, what material is the most hypersealing?
What's the most what?
Water attractive.
Right. Are you saying if you use a higher viscosity fluid, will it work better?
No, I'm saying what disc material would be the greatest, give the greatest adhesion?
The greatest would be a polished surface, like polished stainless. It's not critical, but you want the disc smooth. It's counterintuitive, and a lot of people have done that. They've come in and said, well, that can't work. There's nothing for it to hold on to. I better roughen the surface, right? Or they'll put little dings, like a golf ball. Well, why does a golf ball fly as far as it does? Why do they dimple a golf ball? To break the adhesion. So if you're going to put dimples in these discs, what are you going to do? You're going to break you just defeated it. Right, they've got to be smooth. Why? Good question, we're coming to that. Why did Jake not succeed? These little holes are one of the reasons that he did not succeed, amongst other things. But you'll notice on here that there's a pattern, a bolt pattern around here. And when these discs are put together, it's not real obvious that, go to the overhead, please. It's not real obvious that these geometries exist if you look at the pictures, because they've been polished out. Remember, you want these discs to be smooth as possible. So, not that it would matter on the end disc so much, but you can't see them. But in there is a series of these pins, and there's bolts that go through here. This thing is actually all bolted together. Okay? When this turbine is started, if you don't put bolts in, there's some things that happen. For one, it has no starting torque whatsoever. The maximum torque on this thing is developed when the fluid coming in is half I should say that when the speed of the disk turning is half the velocity of the fluid coming in, that's maximum torque. In other words, you could have this lightly loaded, and this thing will spin up to whatever the speed's coming in. So you're putting in 2,000 feet per minute steam. This thing will run up to 2,000 feet per minute on its peripheral velocity. Okay? Now if you load it, what's going to happen if you don't increase the fuel supply? Fuel supply is kept constant, you put a heavier load on it. What happens? It's going to slow down. Well, it's going to keep slowing down. But as it slows down, it fights back. It keeps trying to turn that thing harder and harder. It resists it. Okay? Because what's happening is you're going to develop additional torque. As it slows down, the torque goes up. So it tries to self-regulate itself. It tries to get back up. But when it finally hits 1,000 feet per second here, what happens? It gives up. The torque curve just drops. So the torque keeps increasing, 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 and you get to 50% velocity, and boom, it just drops off. It stalls, which is not a problem because what would you do with the fuel supply? As the load increases, you increase the fuel supply to maintain the RPM, like any other turbine. Which brings up a good point. On conventional turbines, if you don't control the fuel supply, let's say you put a load on it and it's running nicely with a given amount of fuel coming in at a given pressure, and suddenly the load goes away. What's going to happen to the speed of that disk? In a bladed world, it'll keep going faster and faster and faster until suddenly somebody dies, right? If it's not out of the way. It's a real problem in the bladed world. In this, what happens? It's also going to be a pump, and there's centrifugal forces coming out as well as centrifugal forces coming in, right? Or not centrifugal forces. Centrifugal forces, they're going to match, and when it hits 2,000 feet per minute, it's got as much pressure going out as it's got coming in. So what happens? It self-regulates at that speed, or it never runs away. It's much like a DC motor. You know how you give a DC motor 50 volts, it will go one speed. You give it 100 volts, it'll go twice as fast. You don't have to worry about having a load on it that it's going to run away. It's the same characteristic. Okay? Although on a DC motor, if you have no field and no load, it will run away because there's no counter voltage. But it's very similar to a DC motor in its torque characteristic and its speed. Okay.
But you said something about it won't start.
Exactly. Thank you for getting me back on track. The pins here give you that element of starting torque. These pins now act as an additional torque-producing element in this turbine, and they're essential. If you don't have these pins, you will have drastically reduced performance. What happens on these pins, which has been recently uncovered here in an article, the overhead please. This is an article called The Physics of Tesla Turbine, which was in one of our recent newsletters. And this is Sonny Intrican here, who is the premier turbine builder at this time. Okay, he has really been instrumental in getting this into the commercial market. But anyway, he's looked at this and he says, well, you know what those pins do? They're much like the physics of baseball. When you have a baseball going through the air, what happens is you get these vortices formed on the trailing edge. And these vortices actually are imparting torque to the discs. Okay? So they're actually a torque-producing element in the disc. And when you have a starting condition, you aren't going to have any torque from the disc, so you need those pins. And with those pins, it has tremendous starting torque. You could take your hand and put 100 pounds of pressure on that turbine, and you can't hold it back. Okay? So it does have starting torque. What happened in that Conoco geothermal test, when they had the steam blowing through it, there was no pins. Okay? So there was no torque. That was one of the problems. Okay. And as long as you reduce the load, you wouldn't need a starter. It'll self-start. You could have, and that's actually in that Conoco test. You see a guy over and took the load off and hand cranked it, and it did start. But there was other problems.
Do the pins affect the efficiency
Yes, without those pins increase the efficiency. You're increasing the torque transfer from the fluid to the discs, to those trailing vortices. A lot of people think they'd be in the way. Tesla did too at first. And you can look back at his original documentation, and if you know what you're looking for in his writings, he didn't explicitly say put pins in. That was one of his secrets. I think he was trying to keep that to himself because the patent drawings don't show it either. But if you read how it progressed and how suddenly there was a huge increase in performance and efficiency, that's when he added the pins.
The pins would have about the same effect as the pins, wouldn't they?
It's a different geometry of fluid flow. You have those vortices forming in the trail end and not just random turbulence. It's not just a random effect. It's not like sticking blades in here. I mean, you could do that, but then you'd have a bladed device. They don't get in the way. I mean, there's still enough room for that fluid to vortice around. And I mean, you can't have the pins too close together either. That's a mistake. You say, well, look, some pins are good. Let's put more pins in, right? Some people have done that. It don't work that way because you need that action area behind it to get the effect. How do we know how many pins to use? Because we just follow Tesla's drawings. So you might ask, well, if you didn't put those in the patent drawings, how did we know what was going on? Well, it turns out that he had buried that information in the National Archives in the patent wrappers. And when we dug those patent wrappers up and looked, so I was sitting down trying to make CAD drawings to reproduce these turbines. I was looking at the patent wrappers and looking at the drawings. They're called assembly drawings, which actually shows the pieces that were put together. And lo and behold, I'm going, what is that? And as I looked closer and closer, I realized that those were pins. And once you knew what you were looking for, it became obvious. But everyone had missed it until we came along and discovered it. And once we realized that was one of the missing things, we drew our drawings out. We just had faith at that point that Tesla was on the money. Tesla believed in this, so we were going to try to follow through and make it work. And we just put the drawings out, and we said that anybody want to build this that's a machinist? And we started up the Tesla Engine Builders Association in '93. We put out a membership manual that included the drawings. It's a 90-page manual. It's been updated since. It said, somebody's got to build this. So these guys down in Louisville, which included Sonny Intrican, who I mentioned earlier, got a hold of this. Back to the overhead, please. And they built a turbine.
What's their company name?
They've been through a lot of machinations, but Sonny's company's name is called Intravac. He's a turbine vacuum pumping expert. That's why he's a perfect fit for this.
I came across another website, I'm not sure if it was them or another, they claimed they made some important improvement.
Oh, Frank Germano. Yeah.
Company name.
GermanoIndustries.com or something like that. He was a member, got the information from us, basically. He's talking about some new information that's come out, which I'll talk about in a minute. But anyway, this is an actual disc out of this 11-inch turbine that we have on the overhead. Back to the overhead. And you can see that this disc right here, this is actually a template for the discs. These discs in this turbine are a 32nd. This is more like over a 16th. But what they did is they wanted to save money because they had the disc laser cut, but they have all these individual holes. Laser cut would have like tripled the price or doubled it, something like that. So what they did is they made this template. They put the disc, and then they used these drills as holes as a guide. And once they were done, they gave me their template. Okay? So that's what it is. But this turbine that you saw on the overhead is a high-power turbine. It's got 34, I think, discs in it. It's way overbuilt. It's a 1,000 horsepower turbine if you could get the volume through it. A minimum of 250 horsepower. And the problem is nobody has that kind of energy to put into it. If this is a steam turbine, a 250 horse boiler is huge. So typically what they ended up doing is running it on low power, which still runs well on low power, but any turbine must be sized for its application. And that's where people have fallen down on this technology as well, is they put too many discs in. I mean, the discs are so easy to make that they say, well, hell, let's put more in. That must be better, right? It isn't. Because what happens is you make the rotor wider. And if you don't have enough fluid to drive that wide rotor, the efficiency will drop. Because what happens to the pressure as you make a wider nozzle slot? The pressure will decrease per disc. If the pressure decreases per disc, the torque drops off at a square of the decrease in velocity. It's an exponential function. So that maintaining your velocity on the discs is critical to efficiency. So people have not used pins. They have put too many discs in. That's two of the problems.
Is there an optimal distance between gap?
There is an optimal distance between the discs. We're not recommending that people build this diameter. What's the problem with, if you use this diameter, the ideal is about a 32nd between the discs. As you make the disc larger, you typically increase the space. Okay, Tesla this is an 11-inch. Tesla built a 9 3/4 inch. He had the 32nd spacing. Then he built an 18-inch. I've got a picture of that here. And he had the spacing on that one at 1/16 of an inch. And then he built one that was 4 feet wide, and that was a 1/8 inch spacing. Okay, that turbine I showed you earlier was the 18. Here it is. Here's the 18. You see both those turbines there? Tesla didn't have any way to load these turbines. If you're going to do turbine experimentation for high-power turbines, you need a load, right? Well, he had to make his own dynes. They didn't exist at that time. So what he did is he built 2 of them and put them back to back. Now, he went to the Edison Waterside Station in New York where they had a large steam supply, and he actually operated these things back to back. Now, the covers have been removed. There's actually a cover that goes over it that contains the reversing nozzle. Okay. But he built these dynes and had a very unique way of checking for output. He would run one turbine one direction and drive the other turbine the other direction. Okay, so they're working against each other. And what's between the 2 turbines? A calibrated spring, right. Here's a picture of it with the covers installed. And you notice these handles here? One's up, one's down. Those are the reversing handles. So if you want to reverse the turbine, you can reverse these on the fly, make one the driving and one the driven right on the fly. And of course, the spring between here will twist depending upon the amount of differential and speed and torque between the 2, right? Now what he did then is he had, over here he has a light beam. See up here he's got this light source. That shines down and goes onto the shaft. It will go off the shaft into a mirror, come back off a series of mirrors and come off this other side here. That would come off then onto a calibrated piece of paper, and when it's not running, you calibrate that beam so it's at 0, and as that spring twists, what's going to happen to that light beam? You got a mirror mounted here, and you've got a reflection off of here. As the spring twists, what's going to happen with the light beam? It's going to shift. So you're able to read horsepower, and as long as you maintain the speed constant, you can read the horsepower directly off the scale. Tesla's the first one that ever made a dyne like that, to my knowledge. But he needed to get accurate readings, and this is the way he did it. This turbine developed a maximum of 330 horsepower under test. And the limitation was the steam supply. And also, these were old cast housings. He was afraid that these castings where the steam came in would give. So he was afraid to take it up above 185 pounds of pressure. So at 185 pounds of pressure, it was developing 330 horsepower. Okay? When he ran it at lower pressures, down at around 125 psi, it would develop 200 horsepower. And that's with a free exhaust. That means there's no vacuum, there's no condenser on the exhaust. You always have better performance with a condenser. But with 125 pounds at the nozzle, free exhaust, he was developing 200 horsepower, and that's where he rated it. He rated everything very conservatively. Okay, so the question was the spacing. Yes, the spacing does go up with diameter. Now, what we're suggesting that people build is not the 11-inch, because what's the problem with these smaller diameter discs? As the disc becomes smaller, what's going to happen? So we talked about the spacing, but what else has to happen? Speed has to go up. That's the other problem people have had with this, is that they'll hook this up typically to a 3,600 RPM motor, direct drive. They got a 10 or a 9-inch or even less diameter disc, and they expect to get any kind of efficiency out of it. It ain't going to happen. The commercial bladed turbines that are small diameter, they run upwards of 60,000 to 150,000 RPM. Same thing has to happen here if you're going to get efficiency out of the device. The problem with that is you need either magnetic bearings or specialized air bearings to make that kind of thing work properly. Bearings have been the biggest headache. So how can we get away from that headache? We make the disc larger. As the discs become larger, what happens to the peripheral velocity? As this disc gets larger, what happens to the speed at the periphery? It will increase, right? No, as that disc gets larger, that speed out here is going to be higher than the speed down here. It's got to be. It's going further distance, right? And it's got to be faster. So that allows us to use the same velocity steam, but then to reduce the speed of the turbine. Okay? What we're suggesting to people, if they want to build one of these, and we've got plans now, is for a 21-inch device. A 21-inch device running at about 10,000 RPM will be very efficient. When it runs to full load, it would only be running at 7,000 RPM. And of course, the more lightly you load the turbine, the more efficient it becomes. Because what's happening as you reduce the load? As you reduce the load, the spiral becomes longer. When you're starting it, the spiral, that's why it has very little starting torque. Because when you're starting it, there's almost no action. It just goes right from the nozzle to the exhaust. Okay? But as you get closer to that peripheral speed, the action becomes over a larger area of the disc. And then you get your torque characteristic back. Okay? Questions?
As you go up in speed, the disc will expand. So how much clearance do you need between the periphery and
Good question. As these discs turn faster, especially with the metals that Tesla had to work with, I mean, we're very fortunate today. We've got high-quality stainless. And you really don't need any more than a 304 stainless for this. But there's one thing that happens with stainless, any other metal, is as it runs very fast, what happens? It starts to grow. So his question is, how much space do you have to leave between this disc and the case before you have contact? And that was one of Tesla's problems initially, is that this disc would grow, it would hit the case, and actually start contacting the case. And what we're recommending is 1/8 inch. What Sonny says, who's experts, and he's experimented with these, he's taken them all the way up to 2 inch between the disc and the nozzle, and he said it does not decrease the performance significantly. But he recommends 1/8 because they do grow. But it could also be an advantage, because what if this thing did start to overspeed? It can overspeed if you give it too much fuel. If you keep pumping the fuel pressure up, this thing will keep going faster and faster and faster to meet that fuel pressure. So if you are concerned about that, you could build your turbine such that at a given speed, there'll be an expansion, it will contact the housing, there'll be a brake and slow it back down again. So Tesla actually promoted that as a safety feature. It's the only turbine that can grow, hit the case, and not be damaged. Okay? The amount of abuse that these machines can take is amazing. We had one experience with the 11-inch. Go back to the overhead, please. There we are. Here's the 11-inch all put together. Here's the rotor. Here it is in the casing. It has a variable nozzle. That's worked real well. This is a nozzle you can turn in and out to change the width of the gap here, so you can tune it to whatever pressure you have. That works real well. But anyway, I've lost my train of thought now. What was the question?
Talking about slowing it down.
Oh, we had an accident. That's right. We had an accident with this machine. You see here how it's clamped to the table? Well, what happened is they did not use the bearing frame that we recommended. We recommended that they go out and get a standard pump bearing frame and rework it. Instead, they made their own. They had nothing but problems with their bearings and bearing frame. The biggest problem with this turbine was not the rotor. It was everything they changed. Everything that they deviated from our instruction and Tesla's instruction turned out to be a problem. But anyway, what happened is this shaft, their bearing shifted. The shaft moved forward. When the shaft moved forward, this came forward and contacted the housing. And when that contacted the housing, what do you think happened? It didn't just slow down. It stopped. It's clamped to the table, right? That clamp held. Picked that whole table up into the air and slammed the turbine down onto this face. Just picked that thing right up and hammered it. It had stopped so quickly that the shaft twisted. Okay? But when it hit, it didn't damage the rotor. All they did is pull the shaft out and put a new one in, and they were in business. But just a good thing that nobody was standing between there and the floor, or that would have been the end.
Since we're talking about adhesion and those types of forces, how do you keep the boundary between the housing and the blades such that,
There is no blades.
well, our discs from being, the housing from being a restraint?
You leave us. The question is, how do you prevent the housing from being a restraint? You just simply leave it an 1/8 inch. We're recommending an 1/8 inch. It's enough inches. Oh, side to side? Well, the side to side clearance you want to have as close as you can. They call that run out. If you have a series of discs here, what will happen is that there'll be a slight wobble in the disc as it turns, and you don't want to have it too close because as it wobbles, it will hit the case. So what you want to have is about a 30 thousandths clearance there. And you'll typically get a run out of about 10 thousandths. If it hits the housing on the end, it'll make a terrible scraping noise.
I was talking about the steam. That's what I was talking
What's that? Well, the steam,
about. You're saying it adheres to the stainless steel disc, and that is what it
Oh.
is giving you your torque.
will the end plates act as a brake? Is that what you're saying?
The
No.
housing.
The housing.
The steam is adhering to the housing. How much loss of energy do you have there?
Okay, what you want to do is you want to make the nozzle, where this nozzle comes in and hits the discs, it's a slot. It's a nozzle slot. But you want to make the slot only wide enough to cover the discs, but not any wider than, let's say this is the end disc. You want to make that nozzle wide enough just to hit that area so you don't get spillage. And what you want to do is roughen these discs. The end disc on this, roughen it. The case side, roughen it. That will help break that adhesion. And you also want to have your spacing here correctly. You don't have a wide space. Because it's also a pump, pumping. It's trying to pump out and you're trying to force in at the same time. Okay. You're talking about the labyrinth seals? Right. Can we go back to the overhead again? Yes, Tesla's original patent drawings, he showed something called labyrinth seals. You can see, we put them in there in the first unit because we didn't know if they were really required or not. But they're in the patent drawing. You can see them here. Not really, but they're there. It's little rings that go around here. What happens is you have a ring here, these slots, that mates into these here. It's called a labyrinth seal. But when we investigated, well, you look at Tesla's original units, there was no labyrinth seals. So we figured out what he did. He simply made the nozzle the correct size. And this labyrinth was not made properly. This labyrinth here, that's another mistake they made. Is they didn't want to have this big chunk of stainless that they had to machine down because it would have been expensive. So they took a cheap route and they put a groove in the end disc and put this phenolic in there. They instead machined the geometry into phenolic and then installed the phenolic into the end disc. Well, as soon as they put high temperature steam in there, what do you think happened? They didn't have their nozzle right. They had their nozzle all the way across. So what was happening is that fluid was then getting down between the housings here and the end disc. There was fluid getting in there. And here's the labyrinth trying to block that flow. Okay? But that phenolic did not last very long. As soon as they put high temperature steam on it, just blew it into pieces and out the exhaust. But they've been running it since without the labyrinth, and then there is some loss because their nozzle's not quite right, but it works. It's in all these holes. One's in the center. All the ones around the periphery have this support pins or bolts. It could be rivets, bolts. We typically are suggesting that people use bolts because it allows you to take the thing apart. If you use rivets, it's kind of you're stuck. The other major problem that people have made with this device that was not included in this original one is when you run it on steam, especially saturated steam. Tesla ran these on saturated steam. What does saturated steam mean? Wet steam. In our utilities today, what kind of steam do they use? Superheated. How come they use superheated? Right, these little droplets hit the blades, and they're like bullets. They'll destroy the blades. So in our power plants, they can't let steam turn into saturated steam. This turbine loves saturated steam. And if you're a home power producer and you get yourself a small boiler, I mean, you got enough problems with a boiler as it is to have to worry about your turbine being torn up by the water and the steam. They do put superheaters on these small boilers that are used with turbines, but this, you don't have to worry about water in this turbine. But there's a problem with water in a turbine because the nozzle, when the saturated steam comes in, it will be converted into so a lot of water will occur right there. The water will come out, and it won't go in the rotor. It's just too heavy. It's thrown out. It's thrown out to the periphery. And a lot of people said, well, if the turbine would be great if you could just get rid of that water in there, because what do you think water in there does? It acts as a brake. As a matter of fact, one of Jake Purcell's turbine went to Lawrence Livermore Lab, and they tested it on steam. Guess what their efficiency numbers were? It was less than 1/10 of 1%. Terrible efficiency. What you have to do, and it's kind of counterintuitive, is drill a big hole in the bottom of the case so that water can drain out. People say, well, wasn't that going to cause pressure loss? That's what I would think too, but that's not what happens. The fluid is coming into the disc, it's inside, and you don't have any appreciable loss out of that hole at all. You have 1 or 2 pounds, and that's just enough to push the water out. But the nozzle pressure might be 100 pounds, and on the opposite side, you could have this isn't actually the way it should be. They've modified this sense, but the nozzle would be up here, and you'd have the hole down here. So by the time this fluid comes in, it's already in there, it's already vortexed out. The water flows out the hole at just a couple pounds of pressure. You don't lose your pressure.
Why doesn't the water just go out
It's too heavy. It can't get in the rotor. The rotor's got 2 forces. You know, it won't go in there, and there's forces out and forces in, and it's just too big. So it's pumped out to the periphery and out the hole.
If the water changes from a gas to a liquid while in the plate, then it goes out through the hole?
Right. If the saturated steam converts from water or from suspension from the steam and condenses out inside the rotor, it will go out the center hole.
Inside of the incoming steam.
Right. Once it's inside, it can condense. It'll be forced out. But most of that condensation happens at the nozzle. This question is, will this act as a vaporizer? The answer is definitely. We found that out quite by accident. I'll have to get back to this. I can show you an overhead. This is in our last newsletter. Tesla turbine as vaporizer. There you see the 11-inch again. That's the same 11-inch turbine. Well, what happens is when you look at the geometry of this thing, it's very heavy on this side. There's almost no weight here. So when you transport it, what do you think happens? Thing drops, right? Well, this thing was full of oil. So when they transported, the thing tipped forward, sitting on its nose, and all the oil from this thing ran into this case, filled it halfway up. Okay? So I put air onto this thing, and lo and behold, it just vaporized that heavy oil and spit it right out. Took a while, but it eventually cleared itself. Yes, it will act as a vaporizer. Question?
With the water coming in from the saturated steam, why wouldn't it the still liquid flash?
Why wouldn't it flash to steam?
Yeah, I would expect it to flash to steam.
It doesn't. We know it from empirical evidence. Actually, the first turbine that we discovered this effect on, that we could do this, was this one here. This is John Pickard, one of the guys that developed that first turbine. He made his own steam boiler feeding the turbine. Then he had a surplus B-52 generator here. Here's the boiler feed water pump. And if you look on the bottom here, you can see it. Yeah, you can see it. There it is right there. That's there's a valve there. Right there, there's a valve, and that's hooked up to the bottom of the turbine. Initially, they put a valve there with a little handle, little ball valve, because they thought that they were having problems and they didn't know what to do. So they said, well, let's put a hole and let's open it up so we can clear that water out. When they discovered they could leave the valve open, it didn't matter. That's how that discovery was made. Okay, no question?
1978, we had a group of people at Fermilab and that group project, and the problem was solved with a device where we had an offset rotary expander, vapor motor, swing sliding vane with a steam vapor generator. We had steam at 14 seconds. We used a non-polluting fluorocarbon to produce the steam. We maintained the external temperature of the rotary expander at a constant temperature by putting it inside the vapor generator. So it resulted in the adiabatic expansion principle of the steam. And then when we came in at 12 o'clock with the steam on the rotor, which would be almost zero tolerance, at 6 o'clock we had a way to exhaust that vapor into the next chamber. So we had a two-stage rotary expander motor, external combustion, with a vapor generator using a non-polluting fluorocarbon, which had better properties as far as the thermodynamics.
And where was this turbine experiment done?
Well, it was
At-
after our back room project at Fermilab.
So what was your results? This was done at Fermilab.
The results were excellent. We
So-
ran out of money and we're just sitting on the shelf right now.
So for the benefit of the video who can't hear you, one of the gentlemen in the audience here says that this was built at Fermilab as a.
Don't say that.
Well, you said it. But anyway, it works.
Well,
That's-
it was incredible. We had it 0 RPM with 80 PSI, used air,
0 RPM with 80 PSI with air.
600 foot-pounds of torque.
You had 600 foot-pound,
The torque range.
and you broke your torque wrench at 600 pounds of torque. Did you have the pins?
Yes, we did. We had it ratcheted, and it was the most incredible.
You used the tie pins though, right? You must have had tie pins without the. What-
No, it's not a turbine. This is low RPM, low temperature, massive torque. It is an expander. It's a whole other principle.
Oh, okay, okay.
But I was simply saying that you can solve the problem of maintaining temperature with too soon a condensation by maintaining the external housing with a higher temperature.
I see what you're saying. So he's saying to overcome this problem, use an external housing, and you get heat there and keep it from going into saturated steam.
You can manifold some of the steam
Around it. But in this technology,
as a different technology.
yeah, in this technology, he's talking about the bladed world. But in this, you don't have to worry about that. You don't have to worry about that like you do with blades.
It's a whole other
Right.
deal. It looks the
Right.
same.
Right.
The length, but it's not.
Right. Okay, so back to the overhead, just to give a shot here of the thing running. This is the turbine in operation. Steam coming out the stacks. And just to give you an idea of the scale here, it's not real big. You know, he's taller than those stacks. This is the startup procedure. Initially, you fire up the boiler, and you'll pump all the water through there to make sure you have nothing but water in the steam boiler. Then you start to get steam as the thing heats up, and then you close the valves and put it to the turbine. It's a 2-minute startup. Okay.
What was his efficiency on that?
The efficiency of the single-stage turbine is actually approaching that of small single-stage piston engines. And in the world of steam, small-scale steam, pistons are still the most efficient. This is the only turbine that can come close to the efficiency of those small-scale units. And this unit, like most things John has built, it's way oversized. It's got too many disks for the amount of steam that they were using. They only had like 10 horsepower worth of steam, and again, there's a 250-plus horsepower turbine. That's not the way to do it, but that's the way he does things. So it's still a work in progress. Sonny Entriken, who I mentioned earlier, who built this turbine, he built one of the first high-power turbines. This is a 24-inch diameter runner. He's the guy that wants to follow Tesla to the nth degree and try to make it work. He's the guy that's reproduced this, and he's got enough interest now that this is going to hit the commercial market. They've got enough investment that this is actually going to be put into commercial applications. And that's been the problem. They can't point to anything and say where it's been used. But now that we're into you get the first olive out of the bottle, it's going to take off. Okay. I guess we're running close to time.
Could you comment on what you feel the best applications are?
Well, that's one of the best applications for this is geothermal heat recovery. Tesla in 1931 wrote a thesis called Our Future Motive Power, where he promoted this device for geothermal. There's tremendous geothermal potential in this country, not just in geothermal hotspots. To make this work, all you need to do is sink a deep shaft. Tesla said that this technology would be good for geothermal for a remote home site. So the only thing holding this back is an economic way to sink deep shafts anywhere. But and prime geothermal lands, it's even better. And the advantage of this is you can take the worst garbage salt brine steam like we have in the Southwest. We have lots of geothermal potential, but it's dirty. You put a conventional bladed turbine on there, and it's going to be destroyed. So what they have to do is go to a binary system, where they take the steam out, then they have a primary, and it heats a clean fluid on the secondary. That feeds the turbine. There's a lot of loss and complication on that. Where this, you just take the turbine and set it right on the geothermal source and blow all the crap through it. You don't care. It's not going to be hurt.
Jake was telling me that some experiments where they let the material from down to Salton Sea, which is particularly nasty.
Salton Sea,
They
correct.
let it hit air, they got all kinds of precipitates. When they came up with the idea of keeping a closed system, never letting go to air, it came through completely clean.
What, without particulates? That's not true, is it?
No, that when they opened up the machine later, that there was no accumulations in there. It just
Oh, initially they had accumulations.
because it was reacting with the air.
Oh, okay.
When it just went, the recovered water was just pumped straight back in the
So
ground.
Jake Purcell told you when they used this at the Salton Sea, I don't think it was ever tested there. It was Phelan, Nevada, where it was tested.
He told me about some test of that kind, that the rev was
But it was real dirty coming out. But as long as they don't let it hit air, you said there was no buildup of deposits inside the turbine. Yeah, they have a re-injection well. It comes through the turbine and it's re-injected.
right. In Salton Sea, there's actually a secondary industry where they try to mine those minerals that some of the existing plants are putting out. Huge piles of sodium-rich materials,
This is
tiny nuts of gold.
interesting. Other question?
Has anyone built a fuel-fired turbine?
Good question. Has anyone built a fuel-fired turbine? Well, we go back to Sonny Entriken again. He has built a gas-fired, this is a gas turbine test stand. What he has done is he has a bladed compressor here, or this is a rotary screw compressor. That feeds into the turbine. There's the 11-inch turbine again. That thing's been through hell and has lived. They put extreme temperatures to this turbine without damage. You'll notice there's a line coming in here to the turbine. They do use slight water injection on this. There is water injection here to keep the nozzle cool, just for the nozzle, so you don't melt the nozzle. But the turbine has never been destroyed by heat. They did a mistake and they cut the water off during a combustion test. This is direct combustion now, running on propane, with hot gases coming in here from the compressor. And what happens, the water supply got cut off, and that overheated and destroyed the nozzle and melted the discs. It didn't melt it distorted the discs. All the discs on the very outer edge, at the very outer edge by the tying pin, when that very high temperature came, it warped the discs on the outside. What if you did that to a bladed turbine? Well, on a bladed turbine, you have active moving blades and you have stationary geometries, right? There's very close tolerances, and if there's any distortion in those blades, you'll have a catastrophic failure. In a Tesla turbine, like Sonny says, it doesn't seem to know that they're distorted and doesn't seem to care. It does not affect performance. So you can put so much heat on these discs that you totally warp the outside edge, and it doesn't affect performance. As long as you keep your water injection in there, that won't happen. But they've proven that extreme temperatures, it does not die. It keeps living.
Yeah, I wanted to ask you a question about pumps. On a single-stage pump of vapor material, about what would be an expected ratio of the pressure on the intake side of the pump versus the pressure on the outside?
What would be the pressure on the inlet versus the pressure on the outlet? If you want to come over later and look at the pumping curves, there's just way too much information on this to give you all at once, but we do have all the pumping curves. Go to the overhead, please. And you can get all those numbers. I mean, it's all there, the commercial ones that are available.
Where's that from?
This is our membership manual. Yeah, if you like to join TEBA, it's $35. First year, you get the manual, and the renew is $30, and you get 4 of our quarterly newsletters. So if you want to build, this is the cheapest thing you're going to have. I mean, we figure our 21-inch turbine is going to be about $1,000 to put together if you do it yourself. So the information is the cheapest thing. So don't skimp on the information if you're going to build. But we're out of time, so I'll move to the other room and continue there.
I want all of your questions answered. Jeffrey has been phenomenal. It's just that we do have a set up time frame for our final speaker in this session, and during that time frame is probably going to be another 10 minutes where you should be able to answer any questions that remain. And I also want to say that gotta be one of the best speakers we've had at the conference. Articulate, highly animated, intelligent, persuasive.
Thank you.
A teacher, obviously, stumped many of you with the Socratic method and the questions you didn't know. Yeah, definitely.
Thanks.
Outstanding. Thank you very much, Jeff.
Thank you. And we move to the other room, or you want to go in the hall?